So let's now go over to Excel, and I'm going to make one of my simple tables. So let's have X. What could X equal? Well, if I call up 10 people and I count the number of yeses, which is what X is, or if you want to call it XB, so the number of approves out of 10. So what can XB possibly equal? Could be 0, could be 1. What I'll do is I'll take, if I say 1 plus the previous cell, then I can copy this down a little bit faster. All right, so here are the 10 possible values of XB. Remember, in my little simple tables, we always have a sum. And then let's find the probabilities. So we can, if we didn't know what we were doing, and we wanted to find some binomial probabilities, you'd click on this little fx thing. And this gives us a formula builder window, and we can type in binomial distribution and get some help. And I think I must have misspelled something. D-I-S-T-R-I. I didn't misspell it. I'll just type in binomial, see what happens. I'm stumped on that. Usually it works. We're going to use binomedist, and you'll see that Excel promptly recognizes this and gives us some prompts at the top. So the first argument to this is, how many successes do we want? Well, in this row of the table, we want 0 successes, so that's cell A3. The next argument asks for the number of trials. So trials means how many people do you ask? So the answer is 10. What's the probability of success? Well, 0.86. And then the last argument asks whether we want a cumulative distribution or not. Almost always you want cumulative distributions. Here we don't. So I'm going to say false. So this will give us just raw probabilities. And let's change the format on that number to get rid of the scientific notation. Let's just go to a general number, and I'll give myself about 4 decimal places. At this point, I'm ready to copy. So if I just go to the lower right-hand corner and click on that little dot, I've just copied it down. And we have individual probabilities. Now, just to check our work, notice the probability of 8 successes is 0.2639. If we go back to our sketchbook, that's exactly what we found in part F, 0.2639. So it looks like we did it right, or we know what we're doing in Excel. The other thing to note is that if we add up all of these probabilities, so B3 through B13, they should add up to 1. And sure enough, they do. So we're definitely doing something right. Well, now I'm going to add another column. So let's call these the cumulative probabilities. These cumulative probabilities will also use binomedist. So we'll use binomedist again. And let's fill in the same argument. So the first argument is the number of successes, A3. Out of 10 trials, the probability of a success is 0.86. So everything's identical except this last argument. Now I'm going to say true instead of false. Now this first number, you'll note, is identical to the other one. That's not, it's not an accident. This is just saying that the chance that you get 0 or fewer heads is 0.0000. This is saying that what's the chance that you get 0 heads, which is 0.000. So those two will always match up. I can copy this down, and the very last row ought to be a 1, and sure enough it is. Okay, so this is a cumulative probability table that's just like the cumulative table, cumulative columns that we've had in all of our frequency distributions back in Chapter 3. For example, the age distribution and the number of times at CPK, and so forth. Okay, we're now in a position where we can answer these other questions. So let's go back. Part G asks, what's the chance that you get 8 or fewer yeses? Well, we just go to the cumulative column, and the answer is 0.4184. So I'll go back and pencil that in. 0.4184 is the answer to that. Now, let's look at part H. H says, what's the probability that you get 8 or more? The cumulative column in this Excel sheet does not answer greater than questions. It only answers less than questions. So to use this table, we have to convert this to a less than question using the complementary rule. So notice that this is exactly the same thing as 1 minus the probability that xb is less than or equal to 7. And that's just the complementary rule. So this will be 1 minus, and we can go look up the probability of 7.1545. And if you do the math, this works out to be 0.8455. And so that's the answer. So the chance that we get 8 or more yeses would be 0.8455. If you want to do a little check, you could just add up those 3 probabilities as well. So you could just say this is the sum of these 3 probabilities, 8, 9, and 10. And we also get 0.8455. So that would be another way that you can do it. However, we need to get very good at using these cumulative columns, and that's why I did it the other way. Okay, let's look at part I. Part I is asking about a sandwich probability. I call it a sandwich probability. We want to know the probability that xb is sandwiched between 7 and 9. Well, we need to convert this into some questions that are less than questions. So how do we do that? Well, this is exactly the same thing as the chance that I have an xb less than or equal to 9. Now if I do that, I've overcounted. So I need to, in particular, I don't want 0 through 6, so let's get rid of the probability that xb is less than or equal to 6. I'm now at a point where I can use that cumulative probability column. So let's go back. What's the chance that we are less than or equal to 9? Well, 0.7787. What is the chance that we have 6 or fewer? Well, let's see. 6 or fewer would be 0.0400. And if we do that subtraction, this should be 0.7387. And I think that's right. And again, alternatively, you could just add up those probabilities. So we could do, 7 through 9. So B10 through B12, and you get 0.7387. That's what we got. So either way is correct. We want to get really good at using these cumulative columns because we're going to need them when we get to the normal distribution, and that's why I take you through it this way. Okay, one more thing. We can finish up this table the way we always do by finding the mean and the standard deviation. So let's go do that. What is the expected value of xb? All right, well, to find an expected value, we always take x times the probability of x. So a3 times b3. We can copy this down. And if we add them up, we'll get the mean. So I'll go copy the sum formula, paste it over here. So if you look at that formula, it's just the sum of D3 through D13. It's not surprising that this is equal to 8.6. Now let me make a connection for you. If you go back to the sketchbook, that's exactly what we found to part B. We found the mean to be 8.6. So I just want to illustrate how the binomial is just a special instance of these discrete probability distributions that we talked about around Ed's simple table last time. Let's carry on and find the variance. So the variance, if you remember, is just the probability times the squared deviation from the mean. So 0 minus d $14, let's square it. And I'll copy this down. Now if I add this up, so I'll just go copy the sum business over, I get 1.2040. That should be the square root, or sorry, should be the standard deviation squared. So if I compute the square root of it, I'll get the standard deviation. So let's take the square root of 1.2040, and you get 1.0972, and that's exactly what we got before. All right. Where do we get the 0.86? What we're really doing at this point is forming a new random variable p, which is just a linear combination of xb. So we're taking xb and dividing by 10. So this is going to now give us, oops, got to grab that corner and copy it down. This will give us the percentage of yeses. Let's find the expected value of p. Now to find the expected value of p, I'm going to take p times the probability. If I copy that down, add them up, this should equal 0.86, and sure enough it does. So that just shows where this number is coming from. Likewise with the standard deviation of p. Okay, I would suggest that you try this on your own now.